The Jacobi-Trudi identity expresses Schur functions as determinants of matrices that have homogeneous symmetric functions as entries. There's another identity called the dual Jacobi-Trudi identity that expresses Schur functions as a determinant of a matrix whose entries are elementary symmetric functions. Let's look at that identity, and we'll start by reviewing the tableau that express Schur functions, homogeneous symmetric functions, and elementary symmetric functions in terms of monomials. So recall that the Schur function S lambda is a sum of numbers we called k lambda mu and mu. So if we want to express these in terms of the monomial symmetric functions, these coefficients are called Casca numbers. And k lambda mu is the number of semi-standard Young tableau of shape lambda and content mu. Now, semi-standard means column strict and row semi-strict. So the numbers weakly increase as we go across rows, and they strictly increase in columns. And we wrote the homogeneous symmetric function h lambda as a sum of n lambda mu m mu. So if we're expressing homogeneous symmetric functions in terms of the monomial basis, this is our expression where n lambda mu equals the number of row semi-strict Young tableau of shape lambda and content mu. Again, content mu means mu 1 1s, mu 2 2s, mu 3 3s, etc. And I'm going to write, instead of E lambda, I'm going to write E lambda transpose just because it'll fit well with everything else. So if we want to express the elementary symmetric functions in terms of the monomial basis, the coefficients are m. If we want to express E lambda transpose in that basis, the coefficients are m lambda transpose mu, where m lambda transpose mu equals the number of column strict Young tableau of shape lambda and content mu. So we can see from these formulas the coefficients in the elementary expression have a column condition, the coefficients in the homogeneous expression have a row condition, and the coefficients in the Schur expression have both conditions. So S lambda behaves a bit like H lambda and E lambda transpose. Now, let's look at two special cases of the Schur function. What if lambda is just n? The Schur function s lambda, which is Sn, expands on the monomial basis by being the number of, well, if we're looking at tableau of shape n, there's one row and every column has just one box in it. So the tableau is automatically column strict because it has this shape. So we're just looking at row semi-strict tableau, and Sn, then that's exactly the homogeneous symmetric function. The expansion in terms of monomials is just row semi-strict tableau of shape lambda and content mu. Maybe I could write that sum out. So that means that Sn is just the homogeneous symmetric function Hn, because that's exactly the definition of, well, it's exactly the expansion of the nth homogeneous symmetric function in the monomial basis. Also, if lambda is 1 to the n, so n boxes in a column, then S lambda, which is S1 to the n, is a sum of K 1 to the n mu m mu, where K 1 to the n mu equals the number of semi-standard Young tableau. But if there's only one box in each row, then the row semi-strict condition becomes moot. And we're just looking at column strict tableau. So the number of column strict tableau of shape 1 to the n and content mu. But that's exactly what elementary symmetric functions are. So that means that the Schur function indexed by 1 to the n is just the nth homogeneous, the nth elementary symmetric function. Alright, now let's revisit the Jacobi-Trudi identity. So we defined H lambda to be the matrix that has H sub lambda 1, lambda 2, lambda 3, etc. on the diagonal, and then the indices increase as we go to the right in rows and decrease as we go to the left in rows. So this is a formula for the ij entry of that matrix. When I equals j, this is 0, and we've just got h lambda 1, h lambda 2, h lambda 3, etc. on the diagonal. And then just above the diagonal, j minus 1 is plus 1. We increase the index by 1. Just above that, we increase the index by 2, etc. So the Jacobi-Trudi identity says that S lambda equals the determinant of this matrix, capital H lambda. Now let's define a new matrix, E lambda, the same way, but with elementary symmetric functions. So we'll have E lambda 1, E lambda 2, etc. on the diagonal, and then we'll increase the indices by 1 as we go across. So this will be E lambda 2 plus 1, E lambda 2 minus 1, etc. So it turns out that S lambda is, so the Schur function S lambda is a determinant of E lambda transpose. Now we already observed that S1 to the n is the determinant of E 1 to the n transpose. In other words, the determinant of E n, which is the determinant of this 1 by 1 matrix that just has E n in it, because S1 to the n is equal to E sub n. The proof idea, I'm going to let you work out the details for homework, is that we can let some symmetric function u lambda, which we don't yet know to be S lambda, be the determinant of the matrix E lambda, which is also the determinant of that same matrix transposed. And then we can use tableau to show that the monomial expansion of u lambda is the same as the monomial expansion of S lambda transpose. So thus u lambda equals S lambda transpose. And to do this, you can use the Gessel-Viennot method of having a planar network. And we can position a first source on the left exactly lambda 1 above t first sink. Actually, maybe I'll put the lambda the other way, the arrow the other way. And then we have a a second source on the left, and then maybe a shorter arrow down to T2. And we have edges that are slanted, weighted x1, x2, x3, etc. And all of the arrows on the edges go to the right. So either down and to the right or directly to the right. Again, I will let you work out the details for homework. The end.